This is the second part of the International M2 paper from Edexcel, Jan 15. Looks at a relatively standard statics question. We've got something hinged at A. We'll call them Ry and Rx, split into two components. We've got a uniform rod of 2A, so the weight is mg halfway along the rod, and we've got a weight of kmg at B. And the first part is to show this bit here. Now, normally it's a good idea to take moments about the hinge, and this is no exception. So take moments about the hinge, because the Ry and the Rx are going to come out of the equation. Let's mark some angles on here. We really want to, if we take moments, we want this component here and this component here, because any component in line with it will go directly through A, so it won't have any turning effect. So it's just the bit perpendicular to the rod that has an effect, and F is already only perpendicular to the rod, so that doesn't need to be resolved. Okay, so F is the only one that's going anti-clockwise, so let's write that one first. F times 5 over 4A equals the weight of the rod, the component of the weight of the rod, which is mg cos theta. This is obviously mg cos theta because it's next to the angle that we've marked there. So that's mg cos theta times by A plus kmg cos theta times by 2A. Okay, so that's the that's it. Obviously quite a lot of cancelling going on. I might at this stage work out the triangle. We know that we're told that cos tan theta is 3 over 4, standard 3, 4, 5 triangle. So that gives us that sine theta is 3 over 5 and cos theta is 4 over 5. Okay, so we should be able to now tidy all this up from our moments equation. We can say that F equals, or 5 over 4F equals 2, because the A is going to cancel, mg times by 4 over 5 cos theta plus kmg times 4 over 5 times 2, because there's a 2 there, and A is cancelled. So that, if we factorise, we've got 5 over 4f is equal to 4mg over 5 times by 1 plus 2k. So that gives us 5 over 4 of f cross multiplying is equal to 16 over 25 mg times 1 plus 2k as required. Okay, so that's part A. Part B. Often it's a good idea to get some resolving questions going, particularly if we've got horizontal components here. So if we resolve horizontally, we'll get the horizontal component pretty straightforwardly. Rx is going to be equal to the component of the F force here. We do need to get the angle here, but it shouldn't be too difficult. We've got angle theta here, which must mean that this angle is theta here, because this one is 90 minus theta, so therefore this angle is also theta. So we want the component in this direction, so that's f sine theta. But we already know f from above, so that's 16 over 25 mg times 1 plus 2k times by sine theta, which is 3 over 5. So that's equal to 48 over 125 mg 1 plus 2k. Right. So if we resolve vertically, we'll get, that's part 1. Part 2, we'll just resolve vertically and we'll get the vertical component. But of course we've got a few more forces going on here. We've got the weights coming down as well. So the upward forces is the Ry that we want to find, plus the vertical component of F, which is F cos theta, is equal to mg plus kmg. So Ry is equal to mg plus kmg minus F cos theta, so that's 16 over 25 mg 1 plus 2k, and cos theta we've already said is 4 over 5. Okay, so I think we really ought to tidy this up. It's 125 is the denominator of these two together. So if I times this by 125, I get 125 mg. I get 125 mg, and I'm going to take away 64 because of the 4 times the 16. So that's going to be mg over 125, 61. And then the kmg will be 125 kmg take away 128. So that's minus 3k mg, all multiplied out. So that's that, done. Okay, so part C, it says, given that the force is acting at 45 degrees. Now we don't really need to get too involved with trig here, because 45 degrees is a pretty nice angle to have to work with, because that must mean that the vertical and the horizontal components are the same. This has got to be equal to this. So we've got Ry equals Rx, and we've got some nice tidied up expressions for all of this. So 48 over 125 mg times 1 plus 2k equals to mg over 125 times 61 minus 3k. Cancelling the mg, cancelling the 125. Multiplying out, we get 48 plus 96k equals to 61 minus 3k. So that gives us 99k equals to 61, take 48, which is 13. K is 13 over 99. Okay, not so bad. Relatively standard as these questions go. So let's see what the next question 6 has in store. Question 6 is projectiles. Again, not looking. The scenario was pretty familiar one. Has something been projected from a height above horizontal ground? In these situations, I often think it's nice to use energy when we've just got speeds involved, which we have in first part. So I'm going to use energy. We've got so if we call this V here, half mv squared, the kinetic energy there. If we call this our 0 for potential energy, there's no potential energy there, plus half times m times 7 squared, plus the gravitational potential energy, which is m times g, which is 9.8, but I'll just write it like that for now, times 10. Okay, so m cancels. If I multiply through by 2, I get v squared is equal to 49 plus 20g. Working all that out, 49 plus 20 times 9.8. It's 245. So V is equal to the square root of 245. Which is 15, which I think we would be allowed to give as a third, because it hasn't out, but let's just, we can give almost every possible answer here. We can give it as a third, which is 7 the square root of 5, which was accepted. We can give it as 3 significant figures, which is 15.7. Or we can give it as 2 significant figures, which is 16. Take your pick. Okay. There we go. So the direction of motion as P hits the ground. Now I'm just going to do a diagram here, higher up here. As it hits the ground, we now know, let's use the exact form, that's square root of 245. We know the horizontal component has stayed constant all the way through, which is 7 cos 55. Let's write this the other side now. And we want the direction that this is, let's call it with the horizontal theta. So we've just got a normal triangle there, so we can just say cos theta, because that's what it is 7 cos 55 over the square root of 245. That equals to, when we work out, well, this bit is 0.2565 and a load of other stuff. If I work out the inverse cos of that, that gives me 75.1 degrees to 3 significant figures, so 75 degrees would also be fine as an answer. Okay, part C. Right, just there's a couple of ways of going about this. We can use if we use S equals ut plus half at squared, vertically, then we won't be relying on any of our other answers. So there's some merit in doing it that way. So we can just say S is equal to ut plus half at squared. The vertical component is 7 sine 55. Noting it's gone minus 10 below. So we've got minus 10 is equal to u, which is 7 sine 55 t. The acceleration is obviously minus 9.8 because it's going downwards. So that's minus 4.9 t squared. So we get 4.9 t squared minus 7 sine 55 t minus 10 equals 0. And if we solve that, only what we'll get a positive and a negative answer. We'll get a positive and a negative. Obviously the negative one doesn't apply. We'll get t equals to 2.13 seconds. Again, we can accept 2.1. 2 significant figures is always accepted where g is involved. Okay, so that's question 6. Now on to the last question. So question 7 is a collisions question. We've got 3 particles and we know the masses of them all. We've got P, which is of mass m, Q, which is of mass 2m, and R, which is of mass 3m. it says that they are lying on a line. Particle P has mass. The curve between each pair of particles is E. Particle P is then projected towards Q with speed 3u and collides directly with Q. Then, so that's our before situation. Then afterwards, obviously R hasn't done anything yet, it's still stationary, so it's only between P and Q at this stage. PQ, let's call this V1, and the speed of Q V2, and obviously the masses are M and 2M. So I'm going to find a momentum equation. Momentum before is 3mu. Momentum afterwards is mv1 plus 2mv2, with m cancelling obviously, giving us 3u is equal to v1 plus 2v2. Okay, so that's the first equation. Now let's work out Newton's law of restitution, or Newton's experimental law thing. We're not told what E is, but we're told it's the same in all the collisions. We're going to call it E. Now remember, E is speed of separation over speed of approach. So in this situation, that equals to the speed of separation. V2 is obviously going to be the bigger of the two, so it's V2 minus V1 over U. So let's multiply that out. We get V2 minus V1 is equal to EU. Okay, so we want the speed of Q after they collide. Well, if we add these two together, I'm going to number these now, 1 and 2. So add 1 and 2. The V1's going to cancel there, and we'll end up with 2v2 plus v2, so that's 3v2, is equal to EU plus 3u. So v2 is equal to u over 3, and then it will be E plus 3, which will be our velocity of one of them. Or is it? At the moment. Of course, you can see what's happened here. The actual speed of separation, we're told it's 3u. So we should have a 3 there, which makes it a 3 there, which makes all the e's cancelling. So that just gives V2 is equal to u times E plus 1. Okay, so that's V2. Now if we subtract the two, because it does want both of these, subtract which way around, we want, we've got V2 doubled, so we might as well substitute for V2 because it's a very simple expression. So let's just do that. V2 into the top one, so sub V2 back into either one that we fancy. I'm going to do it into the top one, into this one, so into 1. I could have equally done it into 2. And we have 3u is equal to v1 plus 2u e plus 1. So that's 3u is equal to v1 plus 2eu plus 2u. So that gives us v1 is equal to u minus 2eu, or u 1 minus 2e. Okay. Obviously that might have changed direction, so the speed of it, in this case, because we don't know what E is, really we ought to say V1 is the modulus, because it's asked for speed, the modulus of that, because if E were greater than half, it would have changed direction. So let's leave it like that. Okay, so that's the speed of P. Find the range of values of E for which the direction, I've almost preempted this question. Find the values of E for which the direction of P is reversed. So it's reversed if V1 is less than 0. Okay, so that's 1 minus 2e. Let's call that modulus of E whilst we're at it. So, which is speed. 1 minus 2e is less than 0. Rearrange them for that. That would give us E has got to be greater than half. You might also decide to tell us that E is less than 1, although it wasn't required to get full marks. That was not required. Okay, let's tidy this up a bit and let's get going with part C. So here we've got another collision going on here. We're told that E is 2/3, so it might be worth, before proceeding any further, to work out what V1 and V2 are. So if E is 2/3, V1 is equal to U times 1 minus 2 times 2/3. And that equals minus U over 3. So V1 is indeed reversed. And V2 is equal to U times by 2/3 plus 1. So that's 5U over 3. Okay, so let's just do our before and after situation now. Before, well, our particle, now we know that P has reversed. Let's call that U over 3. And V2 is going with speed 5U over 3 in that direction. Now, we've got, let's make sure we've got R, let's make sure we label everything properly, because otherwise we don't know what's going on. But we're told that R is projected towards it with speed U. Okay, so what we can do is, that's the before situation. Now afterwards, we know that this is moving with speed U over 3. Okay, now I'm going to probably, that's our P. I'm going to still have everything going in this direction, even though we're going to expect these to be negative. V3 is going to go in that direction, V4, but it probably isn't, as we can see, and V4 is going to go in that direction. So we don't have any confusion with signs. I think it's probably easier that way. So we're going to assume V3 is still going in that right direction, V4 is still going in that direction, and set up equations which will conclude that in fact Q is going in the other direction, and if there's going to be a further collision, we would expect that speed of Q to be greater than U over 3. Okay, so that's what we're going to do. So we're going to have to set up our momentum equation and all the rest of it before we proceed. So Conservation of linear momentum. Remember, it's between Q and R now. Almost forgotten the masses of these things. So Q is of mass 2, M, and R is of mass 3M. So we've got 5U over 3 times 2M minus U times 3M, because that's going in the opposite direction here, equals, remember it's these two that we're actually looking at, V3 times by 2M plus V4 times 3M. Now M is going to cancel. Multiply through everything by 3 here, I think. So we'll have 10U minus 9U is equal to 6V3 plus 9V4. So we have 6V3 plus 9V4 equals U. Okay. So now let's set up a Newton's Law of Restitution problem here. We know that E is 2/3, because it's told us. Speed of separation now, well, that's the speed of approach. The speed of separation is obviously V4 minus V3, because V4 is moving away from V3. And they're coming towards each other. So that's going to be 5U over 3 plus U. Okay, multiplying that out, or 2 over 3 times 8U over 3 is equal to V4 minus V3. Multiplying out by 9, we get 16U is equal to 9V4 minus 9V3. Now if I subtract these, if I call this number 1 and this number 2, so if I do 1 take away 2, subtract the 2, I'm going to have 15, because it's 9V3 take away minus 9V3, so that's 15V3 is equal to 16U, or U minus 16U. So that gives me V3 is equal to minus 15V3 is equal to minus 15U. V3 is equal to minus 15U, is equal to minus U. Well, I did say we were going to expect them, going back to I was going to expect the thing to actually be reversed, because that's the only way we could have a collision. But we've got P is going with the velocity U over 3 that we found before. This is going with, for speed U over 3 that we found before. And now Q is going with speed U, but it's reversed in direction. And because U is greater than U over 3, there will be a further collision. And that's it. End of paper. It's taken about an hour in the 2 videos, but I think that's not too bad either. A bit of fiddling around, but hopefully you find it okay. Okay, bye.